Alright, if you have ever struggled to understand unit and dimensions, this video is for you. Kindly sit back, relax, and let's take it gradually. So on the board here, you have serial number, physical quantities, derivations, derived units, dimensions. So we're going to pick those physical quantities one after the other. We'll get their derivations. How do we come up with their units? Then what will even be their dimensions? Sit back and relax and let's take this. Okay, the first one we can pick here, let's pick for instance, you talk about area. Area is a derived quantity. So any unit you have from a derived quantity is called the derived unit. So area here is a physical quantity which is derived. Then area mathematically we have it as what's your length multiplied by breadth. Now length is in meters, breadth is also in meters. Then if you look at this now, you have meter raised power 1 times meter raised power 1, which will give you meter squared. That is from indices m, this raised power 1, raised power 1, that will give you 1 plus 1, which is this. Now we have area to be in meter squared. Similarly, you can have density, which is rho. Density is mass over volume. Now remember, mass here is a fundamental quantity and the unit of mass is kilogram, and volume is length times breadth times height, which will be meters. How many times? 3 times. So from this now you can have the unit as kilogram per meter raised per 3. Similarly again, we can pick the next one, force. Force is the product of mass and acceleration. Mass is a fundamental quantity which has its unit in kilogram, while acceleration is in meters over second squared, meter per second squared. Join this together, this can give you kilogram meters per second squared, and you can call that a derived unit for force. Now, okay, force is in kilogram meters per second squared, but we also know that force is measured in what? Newtons. So that shows that 1 Newton is 1 kilogram meters per second squared. All right, let's pick the next. We can talk about momentum. So momentum here is a product of mass and velocity. Mass is measured in kilogram, velocity is in meters over seconds. So therefore you can have the unit of momentum to be kilogram meters per seconds, inverse of this, or at the same time we can call that Newton seconds. Based on this part, 1 Newton is kilogram meter per second squared. Newton per second also could be the unit of momentum, but 1 Newton is kilogram meter per second squared. Fixed Newton here, which is kilogram meters over second squared times seconds. This takes care of one of these, and that still gives kilogram meter per seconds. Okay, if you want to look at the dimension, to give the dimensions, you are working with 3 of the fundamental quantities, that is mass, which is in kilogram. You represent kilogram with capital letter M. Then you have length, which is measured in meters. You represent that with capital letter L. And you have time, measured in seconds. You represent that with capital letter T. So come back to this table. Let's quickly give dimensions to these 4 derived quantities. This is meters. It means L twice. Then here you have kilogram per meter cubed. Kilogram represents mass, and that is capital letter M, slash meter here is L 3 times, or you can write this as M L raised to power minus 3. And similarly also, we can do that for force. Force here, you can only give the dimension of this. where you have the kilogram, which is capital M, which is meters, will be capital L from here. Then time is seconds. Seconds is to be replaced with capital letter T. Similarly, we can do that for momentum. In the same way, momentum here, you have M again with L with T minus 1. All right, impulse is the product of force, average force, and time. So force is measured in Newton, time is in seconds. If you join this together, you are going to have the unit as Newton seconds. From the last example, that should be number 5. Then you have impulse, which is Newton seconds. 1 Newton seconds is similar to what? 1 kilogram meters per second. So that means impulse, which is in Newton seconds, could also be in kilogram meter per second. Okay. Then the next one, we could pick pressure. And what is pressure? You have your force divided by area. Force is in Newton, area is in meter squared. But 1 Newton is what? 1 kilogram meters per second squared. So anywhere we see Newton here, I replace that with kilogram meter per second squared. So that gives kilogram meters over second squared for the Newton divided by meter squared over 1. So that is same thing as kilogram meter per second squared times 1 over meter squared. Meter here, we cancel one of these meters. Then you are left with kilogram. Then 1 over meter means per meter. 1 over second squared per second squared. So therefore, the unit of pressure is kilogram per meter per second squared, or you can call that Newton per meter squared also. Then you have stress, which is the tensile stress. Tensile stress has the same unit as pressure also, because tensile stress is defined as force also over area. So that covers this, still same thing. So stress also would be kilogram per meter per second squared or Newton per meter squared. Now, that is a very good jam question. You can ask that which of the following has the same units, and then once they have the same unit, they are going to have the same dimension. From example 4 and 5, momentum and impulse has the same unit. So definitely they have the same dimension. And here also you have pressure and stress having the same unit. That means they have the same dimension. Okay, let's check strain. Strain is the ratio of extension to length. Now, extension is in meters, length is also in meters. Meter cancel meters, then you have what? No units. So strain has no unit. Then similarly, you can pick again Young modulus. And Young modulus is your stress divided by strain. So we have that as stress over strain. Stress is force over area. You are dividing that with strain, which is extension over length. Now, at this point, your modulus will be force over area times length over extension. Now, put in the units. We are going to have for force, Newton, for length, meters, for area, meters squared, for another extension here, you have meters. Meters cancel meters. What do you observe? This looks exactly like the unit of stress and also pressure, because you are left with Newton per meter squared, and Newton per meter squared is still kilogram per meter per second squared. Therefore, we can also give the dimension of this. Remember that we are still working with mass, which is in kilogram, and the symbol for that, you use capital letter M. Length in meters, you use capital letter L. Time in seconds, you use capital letter T. Okay, for this kilogram, you have M, meters L, then T minus 1. Similarly, for this also, you have m for the kilogram, L inverse, then x raised to power minus, t raised to power minus 2 again. Similarly for this, you have m, L minus 1, t minus 2, then no units, no dimension. Then here also you have m, L minus 1, t minus 2.